Let us continue with shear force and bending moment diagrams. Again, this topic is relatively simple. In the last class, we saw how to use the free body diagram to get the shear force and bending moment diagram. And using the free body diagrams, we made some rules, which we listed out as rules that if there is any force P acting on all elements to its right, it will cause a shear force equal to P, and so on. So, there were 3 rules we listed, and if you follow those rules blindly, you will be able to solve the problems. Now, there are 2 more things one can see. There is a relation between distributed load W of x, shear force V, my voice is a bit bad today, but anyway, I hope I am audible. Okay. So, if there is a distributed force given by W of x, and the units of this W of x will be force per unit length. You multiply W by dx, that will give you the total load. So, this is a force per unit length. Then what one does is, consider so at a section x from the origin, you consider an element dx. So, this is the element of the beam dx, and on this the load is W of x. Okay. And we draw a free body diagram of this section. Okay. Now, as per our sign convention, on the cut section, what will we get? A force and a bending moment. We assume that there is no axial force. So, if we are talking of shear force. So, now by our sign convention, the shear force on this will be V, and because it is a negative phase, V will point upwards. That is the convention we are doing. In what direction will the moment be there on the left face? The moment will be clockwise, because that is how. So, the moment which is coming here is clockwise M. On the cut section on the right, the shear force will be V plus delta V, and the moment by our sign convention will be M plus delta M. So, this is the total free body diagram of the cut section of the beam, shear force and bending moments on the two sides, and the load acting from the top. And now, to get a relation, what do? We do a force and moment balance. So, on left face, which is a negative phase, V is upwards and M is clockwise. On right face, no, let us write the equations of equilibrium. So, therefore, what we have is V minus V plus delta V okay. So, this leads to delta V is equal to minus W delta x Yeah, just a minute. Yeah. W. W is the load acting on the top. Yeah, it is a variable load W. No, see on this small part, it is W times delta x. See, this is an infinitesimal length. D of W will become a second differential. See, what you will say is it's W on the at x is equal to 0 at x, and then it keeps on increasing. So, it becomes a second order. Okay. So, that is why you take it as infinitesimal length and you say, let us say the average is W. So, W times delta x. So, W in some sense represents the average W from x to x plus delta x, and in the limit delta x goes to 0, it becomes W. Okay. So, that means what we have is that the area under the loading curve, negative of that is equal to the change in shear stress, and this negative sign is coming because of the convention we have used. Okay. Now, of course, this assumes that between C and D there is no concentrated load, because otherwise that would have played its role. So, no. So, that means in some sense we are saying this is C, this is D. Of course, then it can even extend. Once we write it in the integral form, C and D can be anywhere. Now, if we take I am taking moments for convenience, I can take it, I can choose any point. I choose the right hand point so that V plus delta V will not come into the picture. Okay. So, I take moments about D is equal to 0. So, what will I get? M will come, M plus delta M will come, a moment will come because of V, and a moment will come because of W of x. So, let us write all these. Is that clear? There will be no moment because of V plus delta V. Okay. So, we take moments, and when we take moments about D is equal to 0, and we get M plus delta M minus M so, the moment because of V is in clockwise direction. So, minus V delta x minus M plus delta M, and then we will get a moment because of W, and that will be in the plus direction. So, plus W delta x, this is the force. Now, to that we have to multiply depending on the distribution of W. I have put that if suppose W is uniform, then beta will be half. If W is linear, then beta will be 1/3 or 2/3 depending on which end the load is. So, this beta generally beta has to be a fraction lying between 0 and 1 depending on how W is distributed. For uniform W, clearly beta is half. So, therefore, I write it as beta delta x. So, now when we combine all this, what do we get? Delta M plus W beta delta x square, is there are 2 also? No. So, now in the limit delta x tends to 0. Okay. So, the area under the shear force diagram gives you the bending moment. So, we can also use this. Also, one more thing from here you realize is, if V is equal to 0, this implies that dm by dx is 0. Why is this point critical? When dm by dx is equal to 0, what does it tell you about m? That m is either a local minimum or a maximum. Okay? So, when dm by dx is equal to 0, this will mean a local minimum or maximum. And actually, when we are doing this solid mechanics, what are we trying to find from the shear force and bending moment diagram? The maximum value of m, the maximum magnitude. So, which means it will be either the minimum or the maximum, the absolute m, whichever wherever that is maximum, that is the m we have to use to find the maximum bending stress. So, that is why this becomes in some sense a critical point, because that will give you the absolute maximum value of m, or at the boundaries, either at this or at the boundaries. Wherever dm by dx is 0, that will tell you the value of the, wherever v is 0, that will give you the maximum bending moment. So, we find maximum value of the modulus of m from the bending moment diagram, and sigma max will be equal to magnitude of m max divided by s, where s is equal to I upon c. And whatever is the maximum value of sigma, that must be less than or equal to the allowable stress which can be taken. And sometimes in this allowable stress, we will also put a factor of safety to take care of some extra loads. So, to design a beam, the first step is determine sigma allowable for the material from I wanted to write from Google Baba, but I just left it as from some table or chart for that prop material which you may find, and you may use sigma ultimate divided by if the ultimate sigma is given for a material, then you may divide it by a factor of safety to get sigma allowable, because that is just to have an extra this thing. Now we will assume sigma allowable is same in tension or compression. So, this value we will assume it is a symmetric graph. And the second step will be we draw the shear force diagram and bending moment diagram. And we get the maximum value of the bending moment from the bending moment diagram. And third, so now knowing the bending maximum bending moment and sigma allowable, we will get the value of the section modulus, which is minimum. And then, so for example, if we have rectangular beam of timber of depth h and width p, or the ratio h by b is specified, then S is equal to bh square by 6, and this has to be greater than S minimum. So, we work out that the section modulus which we choose has to be able to take that load. And obviously, we choose the value which is just above the minimum value. And why do we do that? Because we want to save on cost. You may of course take a much bigger section modulus and make a beam, but then you are trying to save the cost. So, you are trying to use the minimum material possible which will take that loading. So, that is how design aspects come into play. So, the shear force and bending moment diagram part you probably have done before, or you may not have done, but then using that we have to use those diagrams to design the beam. So, now there may be a, you can check up in the certain, I think there is one particular video in my APL 100 videos also where I draw the shear force and bending moment diagram for a complex case. So, you can have a look at that. We will also, I think, let me see, I think I have an example to take care of this. We will just have a look at this also. But now, there is another way in which one works out particularly, and that is an analytical method to draw shear force and diagrams and bending moment diagrams is using the concept of a singularity function. So, let us define what they are. Now we represent a unit step function, which means if for x less than a, the function is 0 and it is 1 for x greater than a, we call it as a unit step function. And the representation of this is with a unit bracket, with a angular bracket, and since it starts at a, so we write it as x minus a to the power of 0. Now, let us see. So, the generalization of this is f of zeta implies that if zeta is less than 0, then we ignore the function, or f of zeta is equal to 0. And if zeta is greater than or equal to 0, then how will I plot x minus a to the power 1? So, it will be a straight line starting from a of slope 1. Okay. So, here n is equal to 1. So, what we have is x minus a to the power of n is equal to x minus a to the power of n if x is greater than or equal to . And from here what you realize is, if I take an integral from minus infinity to x, so since it behaves like a normal function, I can integrate it and I can also differentiate this. So, this is what I get. An impulse function, we write it as, denote it as x minus a. I did not put it as a power of minus 1, I just wrote minus 1 at the bottom, just to show that what this means is at x is equal to a, if this becomes infinity and it is 0 at all other points. And where would we use this impulse function? To show the concentrated forces and concentrated moments. So, we have at x is equal to, sorry, this is not infinity, this is unit force or unity at x is equal to a, 0 at all other points. So, moment m would be represented by moment of is m times x minus a to the minus 2. So, how do we use these things? Let me just come to this. So, how to use the so if we have a loading like this, which is starting from x is equal to a, it does not start from origin. So, we can express the loading as, because it is uniform, so it is minus w 0 times x minus a to the power of 0. If it is a linear loading, then I will take it as x minus a to the power 1 to the power 2 and so on. So, therefore, we can use this loading, and then dv by dx is equal to minus w, dm by dx is equal to v. So, we can use this sort of a thing. Now, so this part is see, we have started initially, there will be some point load, I have ignored that, I have to put that also, and then if the loading is like this. Now, suppose if there is a portion beyond 2a where there is no loading, then how do you express that? So, you put another, so what you will do is, so to so therefore, now this will become so now to express that overhang part, we will minus w 0 into x minus a to the power 0 will continue up till 3a, but then we add a negative part to counterbalance this extra part. And the advantage of this is then you can use this in programming. So, if you are writing drawing these mentally, then you do not need the singularity functions. The advantage of these functions come in when you want to just feed everything in a code, then you can just put it in form of singularity functions and work them out. So this is particularly not very relevant, but I just thought I will do this. So we use the singularity functions to write expressions for w of x. And we integrate them twice to get m of x. Okay. Now, we have done this. So, this is basically chapter 5. What we have covered till now in the last class and today is seeing the shear force and bending moment diagrams. And you have seen torsion. So, this week you are now going to see bending. So, this part you will not be seeing, the tutorials will not come for this. So, I will take one problem, a detailed problem of this, and I do not have it today. So, I will take it up in the next class, because what I am planning to do is, let me first cover the theory of what I am going to ask you in the mid-sem exam, and the last couple of lectures, that is today I will do some theory, next class I will do some theory, and then I will solve problems. So that those topics which will not be covered in the tutorials, I will solve problems for them. The tutorial sheets and solutions for those I will put up in advance. Now, homework, you have to submit the next homework on Monday, that is on torsion. And the bending homework, at least you should do. I'll probably put up the solutions so that you can see them. So that means so far we'll have 5 homeworks. That will be the 5th homework. I will put up the solutions of all the assignment problems after 5. Torsion one I will put after Monday, but other solutions I will put sometime either this week or early next week. By the weekend I will put up all the tutorial solutions so that you can. The torsion one, we will keep the deadline for the class here so that I can load up the solutions for the other problems also. Okay. So now we will be making a jump, because chapter 6 involves slightly more complex concepts. And what I am going to do here is directly related to shear force and bending moment, and you may find that interesting. So, from chapter 5 of the text, we will move on to chapter 9, which is deflection of beams. Now, there are why deflection of beams becomes important is because there are certain design specifications. If suppose there is a beam running, it can't deflect more than a particular value, otherwise it will cause problems. So, that is one reason. Secondly, what you will realize, and why I find this interesting, is that the indeterminate beams can be solved for by using just as we have seen for example, in tensile loading and all, indeterminate problems can be solved by using compatibility of deflections. So, the same thing you will see we will do here. And the third thing, which is a very general method, is we can use the method of superposition to conveniently and the basis of all this theory is when a beam undergoes a transverse load, then we have seen one over rho is equal to. So, now if m if the moment is changing with x, in pure bending the moment was constant throughout, but if this moment changes with x, then the radius of curvature will also change with x, and the rho which is curvature, this will help us determine the deflection of the beam. We will be able to, and how does this happen? Because rho is related to d2y by dx square, and y is nothing but the position of the beam. Actually, what we have is we have this geometric relation which comes that 1 over rho is equal to d2y by dx square divided by 1 plus dy by dx whole square to the power of 3 by 2. I think this relation you must have done in the mechanics course, and this is just a general mathematical relation which comes, that is how you define the radius of curvature or the curvature rho, and radius of curvature is 1 upon rho. So, now in the limit that the slope is small, and which, why does this slope become small? Because the value of E is very high. So, when the deflection takes place, the values of deflection and slopes are small. So, therefore, we can approximate d2y by dx square is equal to mx upon EI. So, this is the relation which we use. So, now let us see. Now, on this beam we apply So, we had a straight beam on which we apply a uniform load. I am just taking. So, now because of the application of the load, you would expect the shape of the beam will get deflected. And because there is nothing on the right side, nothing is stopping it. So, it will just continue to get bent, and this is, and what exact shape the beam will take will be governed by the equation d2y by dx square is equal to m upon ei. Now, when we apply these type of relations, what will happen is we also will need boundary conditions. Now, what sort of a boundary condition do you expect at x is equal to 0? What will be y at x is equal to 0 after the load is applied? It will be fixed. So, y will stay at 0. If it was 0 initially, there will be no deflection at x is equal to 0. What about the slope? Now, if this is a fixed end, then the slope will also be 0. What about at x is equal to L? What will happen to the deflection? Will we have any condition on deflection? We will not have, because deflection can be anything and the slope can be anything depending on the load. But do we have some condition on shear force at x is equal to L for a beam like this, and on bending moment at x is equal to L? What will be the shear force and bending moment at x is equal to L? You cut the beam from the right, just cut a very small section. What shear force will come there? 0. What bending moment will come there? 0. So, on the right part, on the extreme end, you do not have any condition on deflection, but you have condition on shear force and bending moment. Now, suppose if it was a simply supported beam, that means two reactions, we can draw that. So, let us just first complete this discussion. So, let this be the end A, let this be the end B. So, here what we know is y of A is equal to 0 and dy by dx at A let us first talk of deflections only. I will talk of the shear force bending moment. bit later. Let us look at a beam like this. Some simple beams I am taking. Load P. So now of course, these are much exaggerated. The deflections won't be this much, but this is the expected shape if you have a beam like this. Now, what are the boundary conditions you have on A and B? After deflection, what is y at A and y at B? They should be 0 because these are fixed ends. If a load is being applied, so y of A will be 0, y of B will be equal to 0. You will not be able to get anything on the slope. Slope will be determined by the equations of the beam, but you will get y is equal. So, these are the type of boundary conditions which come in from the geometry. Okay? Now, in this case, no boundary condition is available on theta A and theta B. Now we have d2y by dx square. We integrate this twice. Now, what you realize is, suppose we take a very simple case. If I look at the bending moment diagram, at A, I will get a reaction which will be P times some fraction of P. At B, I will get another reaction. So now when I draw the bending moment diagram, the shear force diagram will, so from A to D, the bending moment diagram will have the same m of x. And then because there is a change at D, the bending moment diagram from D to B will have the same analytical expression, but it will be different from that of A to D. So that means from A to D, I will get an equation which will be y1 of x. And from D to B, the equation of deflection will be y2 of x, because m of x is changing. The form of m of x changes because, so this is because expression for m of x changes at D. Now, when we integrate a second order ODE, we will get two constants of integration. So that means we will get totally in this, we will get four constants of integration, 2 from y1, 2 from y2. Now, what are the boundary conditions we have? We have only two boundary conditions, y of a is 0, y of b is 0. Which are the other two boundary conditions we will get? How will we solve? The deflection. They will come from the fact that at D, the middle point, the point where they are, the beam has to have a continuous shape. So, the slope and deflections will be equal, which means y1 at D is equal to y2 at D, and theta 1 at D Okay. So, this is how you will be able to solve all statically determinate problems. Let us take an example. A 9-meter long beam So, we have this beam like this, and we want to find the deflected shape of this beam. So, the beam starts, there are two supports, it is a overhang beam in the sense that it is extending beyond the second support. We have let us say A, B, C, D, whatever points we call them. Let us call this as A, let us call this B, let us call this C, let us call this B. So, AD is a So, the first step in solving this beam is, let us draw the So, the first step in the solution will be to find A y and C y, which you can easily do. Okay? I am not going to work out. So, this you get by doing this. So, now let us try to draw the shear force diagram. So, we have a 1 kilonewton force. So, how will the, let me just draw the loading here. So, the shear force diagram, there is 1 kilonewton. So, we go 1 kilonewton and write, then this is the, can everybody see the shear force diagram? See, you should be, at least for cases like this, you should be able to draw the shear force diagram directly. And I have just followed the rules, starting, just going through the details. Starting from A, there was a force of 1 kilonewton. So, on all sections to its right, we will have plus 1. Then the next eventful point is point B. At point B, we have a force of minus 4 kilonewtons. So, on all sections to its right, it adds minus 4. There is already a plus 1. So, it becomes minus 3. That continues till point C, where we have a plus 5 kilonewtons. So, from minus 3, we add 5. So, we go to plus 2. And that continues till the end, where there is 2, and therefore, it stays at 2 till the end. Is that clear? So, this is how the shear force diagram looks like. Now, how will the bending moment diagram look like? So, bending moment diagram, is area under the shear force. So, it is 1. So, it will be 1 times x till x is equal to 3. Then at the point it starts to go down. What you can do is, in the bending moment diagram, calculate the value of the bending moment at the critical points, and then you know it is linear, so it will just go linear. So, from B to C, what you will get will be, it will have a shape like this, and from C to D, it will come to like this. So, this is A, this is B, this is C, this is D. And for 0 is less than x is less than 3, m is equal to 1x, see again, while writing this, I have first drawn the diagram. I should not have done this. I should have first written the expression. See, from 0 to 3, what is the rule? Any positive force causes a positive bending moment equal to P times zeta. So, it is equal to, on all sections to the right of A, the bending moment contribution will be 1x. Now, once I reach B, there is a force of minus 4. So, on all sections to its right, it will be minus 4 times the distance, and the distance is now x minus 3, what we called as zeta. So, it will be x which came from earlier minus 4 times x minus 3. And what I can do is, at x is equal to 6, I calculate its value. So, what is the value at x is equal to 6? 6 minus 3 is 3, minus 4 into 3 is minus 12, and to that I add 6. So, it is 5 minus 5. So, the value of this will be minus 5. Then from 6 to 9, what is the value of m? Okay, now can somebody tell me what will this be? X minus 4 times x minus 3, and what do I have to add to this? What is the force at C? Plus 5. So, what do I add? Here, what do I add? Sorry about this. Plus what? Or 5 times x minus 6. Does everybody see this? This is how, this is of course a simple case. So, we draw this. Now, given this bending moment diagram, if the bending moment is like this, this is the expected shape of the beam. Up आ जाइए. Okay. And the concavity of the beam will, so I'll take up one more example from here onwards. Okay.